I want you to picture a Jenga tower. You know, you've got this tall, meticulously stacked tower of wooden blocks sitting on a table.
Right.
And it looks incredibly solid. I mean, almost permanent. But the entire premise of the game is to pull out just one block at a time. And when you do that, well, one of three things usually happens.
Yeah, sometimes you slide a block out and the tower just stands there. The structural integrity holds.
Exactly. The missing piece doesn't seem to matter at all. But then other times, you pull a block and the whole structure wobbles.
It shifts, maybe leans heavily to one side.
Right. But it manages to stay upright in this new, slightly more precarious shape. And then there are the times you pull out that one crucial block and the entire thing just violently collapses into a pile of wood.
Yeah, and that visual perfectly encapsulates what we're analyzing today. I mean, ecosystems, as massive and ancient as they might seem to us, they're governed by those exact same mechanics of structural dependency.
And that is the mission of our deep dive today. We're exploring how a single change to one localized part of an ecosystem can send just massive ripple effects through entire populations.
It's fascinating.
It really is. Now, our sources today basically cover the foundational framework taught to, like, 7th grade science students studying ecosystem dynamics. But what's so wild is how rapidly those basic rules scale up into mathematical chaos when you apply them to the real world.
Oh, absolutely, because the principles of ecology, well, they don't care about the scale. Whether you're looking at a drop of pond water or, the entire Amazon basin, ecology is simply the study of interactions between organisms and their environment.
Yeah, it's about mapping the system. I always think of an ecosystem as this incredibly complex engine. You've got gears, belts, fuel lines, combustion chambers.
Lots of moving parts.
And even a tiny, seemingly insignificant loose screw can change the entire thermodynamic output of that engine. So if you've ever wondered why field scientists panic over a 1-degree temperature shift or the arrival of a single invasive bug, you're in the right place.
Definitely. But before we can understand how the engine breaks down, we need to categorize the parts, right?
Makes sense.
So the sources divide the fundamental building blocks of any ecosystem into two broad categories. You have your biological components and your physical components.
Let's skip the basic definitions here. I mean, we all know what plants and predators are. The biological or the biotic components, they aren't just a static list of animals living in a forest.
No, not at all.
It's the sheer pressure they put on each other. We're looking at producers, consumers, and decomposers, sure, but also the intense competition for resources.
And things like the introduction of invasive species or the spread of disease.
Right, and human activity.
Oh, humans are absolutely a biological component. Industrial logging, urban sprawl, introducing non-native crops, those are massive biological disruptions.
Yeah.
But those living entities, they are entirely at the mercy of the physical or abiotic components.
The non-living blocks of the tower.
Exactly. Those are the underlying environmental conditions that dictate whether biological survival is even permitted in the first place.
So we're talking about what, like temperature gradients, water availability?
Yeah, water, sunlight penetration, the specific chemical makeup of the soil. And in aquatic systems, it's stuff like the salinity of the ocean, ocean currents, or sea ice coverage.
Okay, got it.
It also includes severe physical events, think wildfires, seasonal storms, and chemical pollution.
Now, here's a concept that really shifted my perspective. When we look at a forest or a lake that hasn't changed much in our lifetime, we tend to think of it as stable.
Right. People equate stability with stillness.
Yeah, we assume a stable forest is just this frozen museum diorama where nothing has happened.
And that is a fundamental misconception. The concept of a static balance of nature is actually an outdated myth. Scientists use the term dynamic equilibrium.
Which kind of sounds like an oxymoron.
It does, but it beautifully describes the mechanics of a living system. Even when an ecosystem appears perfectly stable to the human eye, there is intense, continuous action at the ground level.
Give me an example of that.
Well, energy is flowing continuously from the sun, right? It's converting into biomass, moving up the food chain. Matter, like the actual atoms of carbon, nitrogen, phosphorus, is cycling endlessly between living tissue and the soil.
Right. The decomposers are always working.
Exactly. Birth rates are rising to perfectly offset mortality rates. So the system is moving at high speed, but the inputs and outputs are just currently balanced.
It makes me think of riding a bicycle.
How so?
Like, if you watch someone riding a bike in a straight line down the street, they look perfectly stable. But to maintain that stability, the rider is constantly making rapid microscopic physical adjustments.
Right, shifting their weight.
Yeah, micro-correcting the handlebars, adjusting their pedal cadence just to stay upright. If they stop making those active physical adjustments, the bike just falls over immediately.
That is a great analogy. The ecosystem is always pedaling. It's constantly absorbing small disturbances, a dry summer, a harsh winter, maybe a localized fire, and it's adjusting its internal components to stay upright.
And that capacity to absorb a shock and rebalance, that's what ecologists call resilience, right?
And nailed it.
But what happens when a shock is just too big? Like, let's take this out of the abstract and look at what happens when a Jenga block is actually removed from a real system.
Okay, well, our sources highlight several real-world field examples from Alaska to illustrate this. When measuring an ecosystem's response to a disruption, we generally categorize the consequences into direct effects and indirect effects.
And the direct effects usually come down to caloric resources.
They do. A population size is fundamentally governed by the availability of fuel. I mean, organisms need biological energy to survive and reproduce.
Right.
So if a resource population, the prey, shrinks, the consumer population suddenly faces a massive caloric deficit.
Okay, let me push back on that for a second. If a specific prey population shrinks, why does the predator population automatically drop?
What do you mean?
Like, predators aren't mindless machines, right? Can't a wolf or an eagle just adapt and hunt a different animal? Why does their population plummet instead of just shifting its diet?
That's a really good question. It comes down to a concept called optimal foraging theory. Hunting costs energy. A predator has evolved to hunt a specific type of prey efficiently.
Okay, so if their primary prey disappears...
They have to hunt secondary suboptimal prey. Maybe it's harder to catch or smaller, or maybe it fights back harder. Suddenly, the predator is burning more calories to catch the food than the food actually provides.
Oh, wow. So they are operating at a net caloric loss, even if their stomach is full.
Yes, and when an animal operates at a caloric deficit, biological mechanisms kick in to prioritize basic survival over reproduction. Females just cannot carry pregnancies to term.
That makes total sense.
Yeah, litter sizes shrink from 5 to 1. Infant mortality spikes because the mother can't produce enough milk. The population drops mathematically because the birth rate completely stalls out.
That paints a much clearer picture. It isn't just predators starving to death in the snow. It's the sheer mathematics of reproduction failing due to, basically, energy economics.
Exactly.
So that's a direct effect. Let's talk about the indirect effects, where the food web gets tangled.
We call these trophic cascades. A perfect demonstration of this is the coastal Alaskan ecosystem, involving sea otters, sea urchins, and kelp forests.
This is such a classic example of an indirect biological disruption.
It really is. So sea otters are an apex consumer population, right? And their primary fuel source is the sea urchin.
Okay.
Sea urchins are benthic consumers that graze on kelp. And kelp is the producer, it anchors the entire underwater forest.
Right.
But historically, the fur trade caused the sea otter population to just completely collapse.
So we remove the otter block from the tower.
Right. The immediate direct effect is that urchins lose their primary predator. So the urchin population explodes exponentially.
Because nothing is eating them.
Exactly. But the indirect effect is the mechanical destruction of the environment. Urchins don't just nibble on the leaves of the kelp. They graze along the ocean floor and chew straight through the holdfast.
Holdfasts.
Yeah, the root-like structures that anchor these massive 80-foot-tall kelp stalks to the rocks.
Oh, so they are essentially cutting down the trees at the trunk.
Precisely. One urchin chewing a holdfast could detach an entire kelp plant, which then just washes away in the tide.
Wow.
So millions of unchecked urchins will effectively clear-cut a dense underwater forest in a matter of months. It leaves behind this barren, rocky wasteland.
That is wild, because the otters and the kelp don't even interact directly. Otters don't eat kelp.
Right. But the removal of the otter indirectly triggered the total collapse of the kelp forest.
Okay, so we've been looking at a biological change. What does it look like when the physical foundation of an ecosystem shifts?
For a severe example of a physical disruption, we can look inland to the Alaskan tundra. The defining abiotic feature of the tundra is permafrost.
Which is frozen soil, right?
Yes, a deep layer of soil, gravel, and organic matter that remains permanently frozen beneath the surface. Above it sits what we call the active layer.
Okay, what's that?
It's a very thin margin of topsoil that thaws briefly in the summer, just enough to support low-growing mosses and lichens, and then it refreezes.
But global temperatures are rising, so that is our physical disruption to the system.
Exactly. As atmospheric temperatures rise, the summer heat penetrates deeper into the soil. The active layer expands downward, and the ancient ice within the permafrost begins to melt.
So the actual ground they are standing on is melting.
It alters the topography completely.
Yeah.
When the subterranean ice turns to water and drains away, the soil structure collapses into the void.
That sounds disastrous.
It is. It creates massive land slumps, sinkholes, and newly formed lakes called thermokarst. You'll even see phenomena known as drunken forests.
Drunken forests.
Yeah, shallow-rooted trees are suddenly tilting at severe chaotic angles because the solid ground beneath them has literally turned to mud.
Man, the physical landscape is literally deforming. But how does that trigger a biological cascade? Because the sources mention a phenomenon called the greening of the Arctic.
Right, so it creates a dangerous biological feedback loop. As the permafrost thaws and the soil warms, the biological constraints of the tundra change. Areas that historically only supported low, dry lichens are suddenly colonized by tall, fast-growing deciduous shrubs.
I mean, shrubs moving north doesn't sound inherently catastrophic on the surface.
You have to look at the mechanisms of heat transfer. The tundra is naturally covered in snow for most of the year, and snow is highly reflective, right? It bounces solar radiation back into space.
Right.
But these new, taller shrubs poke up above the snow line. Their branches and leaves are dark, so they absorb the sun's heat instead of reflecting it.
Ah, the albedo effect. The dark shrubs act like a black t-shirt on a sunny day.
Exactly. They trap the heat. That heat radiates down the stem of the shrub and warms the soil directly around the roots, which accelerates the melting of the permafrost.
Which allows even more shrubs to grow.
You got it. A slight shift in the abiotic temperature allowed a new biotic competitor to enter, which in turn typically altered the temperature of the soil even further.
I want to clarify how these changes ripple out to the animals living in that transitioning landscape, though. Imagine you have two completely different species of insect-eating birds living in this newly warming tundra.
Okay.
And they're both competing for the exact same species of caterpillar. If a physical change in the environment suddenly causes bird species A's population to double, does that mathematically force bird species B's population to shrink, even if the two birds never physically interact?
Without question, this is the mechanism of indirect competition. Bird A is now consuming twice as much biomass from the caterpillar population.
So the caterpillars are depleted.
Yeah. Bird B now has to spend twice as much energy flying around trying to find the few remaining caterpillars.
Yeah.
So bird B enters that caloric deficit we discussed earlier.
Its birth rate drops and its population shrinks.
Exactly. The two bird species never fought over a nest, but bird A's success starved bird B by draining their shared resource pool.
It is entirely mathematically linked. But that brings up a massive logistical problem. I mean, it's easy for us to sit in a studio and outline these clean, isolated variables. But ecosystems are chaotic, overlapping webs of millions of organisms. How do field scientists actually prove what caused a population to change? You can't just walk into a dying forest and magically deduce that a temperature shift caused it.
No, you can't. And proving causation is the core challenge of modern ecology. You can't put an entire biome in a sterile laboratory. And it's physically impossible to count every single organism in a population.
Right, you can't track every beetle or every blade of grass.
So how do they build an empirical argument then? They rely on rigorous statistical sampling. Scientists establish plots. These are small, strictly measured representative areas within the ecosystem. They meticulously count the individuals, measure the biomass, and track the soil chemistry within that specific plot over long periods. And then they use complex statistical models to extrapolate that data across the entire ecosystem.
Oh, it's like looking at a high-resolution digital photo, but you're only allowed to look at 100 random pixels.
That's a good way to put it.
If 80 of those scattered pixels are blue, you can mathematically extrapolate that the picture is likely of the sky.
Yeah.
But if your sample size is only 3 pixels, you might accidentally sample a white cloud and incorrectly assume the entire photograph is solid white.
Exactly. You need a massive continuous sample size to see the real picture. Ecologists spend decades compiling observation records, population graphs, and satellite field mapping just to establish a baseline.
So you have to mathematically prove what the dynamic equilibrium normally looks like before you can definitively prove that a disruption is actually occurring.
Right. And the field tools they use to gather that evidence are staggering. We aren't just talking about scientists with binoculars and clipboards anymore.
What are they using?
They are analyzing the environment at a microscopic structural level. Modern ecologists don't just track animal movements. They track the physical flow of matter through the ecosystem. One of the most fascinating diagnostic tools is dendrochronology.
Analyzing tree rings. I always thought that was just a way to count how old a tree is.
Oh, it's so much more. It's like a highly detailed environmental hard drive. Trees add a new layer of wood, called the cambium, to their trunk every single year.
Okay.
The thickness and cellular structure of that ring are directly dictated by the environmental conditions of that specific year. By extracting core samples from ancient trees, scientists can read centuries of physical data.
Walk me through the mechanism of that. How does a biological event, like, say, a beetle outbreak, leave a physical scar inside the wood?
Well, when a population of defoliating insects, like spruce beetles, swarms a forest, they strip the canopy of its needles, the tree suddenly loses its photosynthetic engines.
It's starving.
Yeah. To survive, the tree abandons radial growth and diverts all its remaining energy to defense mechanisms, like producing sap to pitch out the beetles.
It stops growing to fight the infection.
Precisely. When you look at the cross-section of a tree that survived that event, you will see a sudden, dramatic cluster of paper-thin growth rings that might span a decade.
Wow.
By cross-referencing thousands of trees across a region, scientists can map the exact geographical spread and intensity of a beetle outbreak that happened 300 years ago.
That is incredible.
They can then overlay that biological data with historical temperature models to prove how climate oscillations drive insect populations.
So they're literally reading the forensic history of the forest.
Yeah, they are.
But the methodology that absolutely fascinated me from the sources is stable isotope analysis.
Yes. Mass spectrometry applied to the food web. It revolutionized how we trace indirect ecological connections.
Walk me through the actual chemistry of this, because it proves a connection that honestly sounds impossible.
Sure. Elements like carbon and nitrogen exist in different forms called isotopes, which vary slightly in atomic weight. For example, nitrogen-15 is heavier than the more common nitrogen-14.
Tracking with you so far.
Because of complex atmospheric and biological filtering, marine environments accumulate a much higher ratio of the heavy nitrogen-15 isotope compared to terrestrial environments.
Wait, so the ocean literally carries a different chemical signature than the forest?
It does. Let's look at the Alaskan salmon. Salmon hatch in freshwater streams, but they migrate to the ocean where they spend years packing on biomass. They're absorbing marine nutrients, filling their cellular structure with that heavy marine nitrogen-15.
And then they swim back upstream to the forest to spawn.
Right. They swim deep into the terrestrial ecosystem. Brown bears and bald eagles congregate at these streams, consume the salmon, and drag the carcasses deep into the woods.
Okay, I see where this is going.
The decomposers, the fungi and bacteria, they break down those carcasses, releasing the marine nitrogen directly into the forest soil.
And the tree roots absorb it.
Exactly. When scientists run leaf tissue from a deep forest Sitka spruce tree through a mass spectrometer, they find overwhelming concentrations of marine nitrogen-15.
That is wild.
They can chemically prove that a tree growing miles inland is physically constructed from atoms that were foliaged in the ocean.
They're tracking the flow of physical matter across the boundaries of ecosystems. It provides undeniable empirical proof of these massive food web connections.
It proves that the biological consumers, the bears and eagles, are operating as physical conveyor belts, transporting thousands of pounds of marine fertilizer uphill into the forest canopy.
It fundamentally changes how you look at a landscape. And as we wrap up this analysis, we want to give you, the listener, a practical framework to use. We want you to take this out of the theoretical realm and apply it to the physical world around you.
Yeah, whether you're managing a national park or just walking through your neighborhood, you can analyze your environment like a systems engineer.
Exactly. When you notice a localized change in nature, challenge yourself with a 3-part diagnostic reflection. Step 1. Isolate the variable. What exactly changed?
Was it an abiotic disruption, like a new concrete parking lot altering the drainage of a local creek? Or was it a biotic change, like an influx of a newly introduced predatory insect?
Step 2. Trace the impact. What population was affected? You have to look past the immediate victims. Was a consumer population forced into a caloric deficit?
And more importantly, what indirect trophic cascades might result from that deficit? If a predator disappears, what herbivore is about to overgraze the landscape?
And finally, step 3, the most critical step for rigorous scientific thinking. Demand the evidence. What empirical data supports your claim?
Right. Are you observing a physical change in the topography, like a thermokarst slump? Are there long-term sampling records or isotopic analyses that can mathematically prove the connection?
This framework forces you to stop looking at nature as a static backdrop and start seeing it as a dynamic, highly pressurized network of interacting variables.
It's all connected.
Which brings me to a final thought I want to leave you with today. It's something I've been analyzing since we discussed those salmon isotopes. If ecologists can use mass spectrometry to mathematically prove that the nitrogen from a deep ocean fish is physically building the wood of a terrestrial forest tree, where does the ocean ecosystem actually end?
That's a profound question. Our definitions of biomes are human constructs. We draw lines on maps to make the complexity digestible.
But are the boundary lines we draw around ecosystems completely arbitrary? If a heavy nitrogen atom can flow from a marine current into a fish, into a bear, into the soil, and finally into the leaves of a tree, it suggests the boundaries don't exist. The blocks we pull from the Jenga tower don't just destabilize the wood on the table. They vibrate the table, the floorboards, and the foundation of the house itself. It forces us to realize just how violently interconnected the entire machine truly is.